We will have another one around 4 o'clock. And I'd like to start with the second section of presentations. And I'm glad to be able to welcome Professor Dr. Dieter Stapf. I hope he's already online. He's head of technical chemistry at the Karlsruhe Institute of Technology, KIT, and he specializes on pyrolysis and techno-economical process evaluations. And he will give us a technical assessment on synergies between mechanical and chemical recycling, because they are not necessarily competitors, but they could be complementary. Mr. Stapf, I hope you can hear us. Can you hear us? Great. Don't forget to unmute yourself. And I'd like to ask you to give us your input on mechanical and chemical recycling. How are they related?
Well, thank you very much for the friendly introduction. Actually, I would like to give a few points of complementation from the point of view of the scientific point of view on chemical recycling. We always discussed about mechanical and chemical recycling and how they can complement each other. And this is exactly what I'm going to focus on in my presentation. So please give me the first slide. Okay, so plastic waste. We have focused very much on packaging waste, but there's so many other plastic waste kinds, rotor blades of windmills. We've talked about that. So you can see that on the picture. So the collection of lightweight packaging that are then mechanically sorted. Then packaging waste, of course, in Germany today make out almost half of all plastic waste, but the plastic waste is only the half of the produced plastic volume, and that is because many plastics go into long living plastic products. So, for example, insulation materials in buildings, commercial waste, which is short living, and then we have electronics and electrical products. We have the automotive industry. Cars have a large plastic share and fraction. Of course, we do have to deal with those as well, because many of them cannot be mechanically recycled at all, because they are combined materials that have effect products, also flame-resistant materials, which cannot be sorted and cannot be separated, and that's very important for chemical recycling. So let's talk about the top right corner, and that's what we've seen frequently today, which is the lightweight packaging. So let's have the next chart. And we do see here the entire chain, how it is being handled today in Germany. So we have the collection systems, they have the packaging waste, yellow bag. They are being sorted, and then we have the recyclates, and the major share or lion's share goes into incineration. It can be mechanically recycled and then give it into chemical recycling. We have the example of pyrolysis. There's also gasification, but today we're talking about pyrolysis. There's always three products, one gas, which for plastics waste is very attractive, then the desired product, which is the pyrolysis oil, and a solids fraction, which has carbon, but also all the other anorganic chemicals which cannot be mechanically sorted and is being captured. And then we've seen the oil, which is the chemical feedstock on the right, and then we have the gases from pyrolysis, which can be used just equally well as chemical feedstock. It's not so much in terms of volume, but it can be well used. And the solids actually go into an energetic recycling. It's a smaller share, a smaller fraction, and we saw the products, they are being upgraded in order to be used as a steam cracker, feedstock, or naphtha. So chemical recycling as a large separator of materials. And often people ask, what's the energy need here? If you look at styrene, for example, and pyrolyze that, chemically, physically, you can calculate what the energy demand is, and we measured it for the waste, all kinds of waste that we took here, and you can see for all these fractions, the respective energy demand for heating, melting, pyrolysis, and evaporation. That's the entire process of pyrolysis. And then this divided by the energy input of the waste. So you see that we're always between 10 to 14% of the energy input, which means the other way around, 80 to 90% are afterwards in pyrolysis, or I'll keep being energy, so they go into the feedstock that can be reused, and that's the research target. So that's 80 to 90%. So energy demand exists due to the temperatures, logically, and if you take the solids of pyrolysis, you get the necessary energy in order to operate the process. You have an energy autarky and a very low energy demand. And this is why you do not have to translate so much during the pyrolysis process. So the next picture, I said that I will talk a little bit about a technical assessment in the life cycle analysis. In the first part we've already of the conference, we've already seen that. So what we can see here is comparisons between mechanical, chemical, recycling, and a combination of both, producing new materials from crude oil based materials, naphtha. So you can see naphtha, which is the standard process. To make new plastics, we have mechanical recycling, for example, taking LWPs, then you have a pre-treatment, it's a pre-sorting process. There are these arrows, black means that you capture metals, and red means that mineral fractions are being captured. And then you have a sensor-based sorting plant with which you get the recyclate after a further treatment. Here it is a regranulate, which is what we called it. It's plastics which, in terms of quality, have a different kind of quality than the virgin material. In the middle arrow, of course, instead of sorting, you could put everything into chemical recycling, but we don't want to do that. And this is why we have the last path at the bottom, and that's exactly what I showed you before, namely sensor-based sorting, which is easy to capture and has a reasonable quality, standard quality, which results into secondary plastics. For example, a food grade packaging, you can, according to German law, a detergent packaging, and the rest ideally could be used for chemical recycling, and then that leads to new virgin material. So we compared these different paths, and I'm talking about material stream and energy stream analysis, similar to what we use for LCA. And I'm going to show you one detailed picture for chemical recycling, and that's the next chart. I do not want to keep it too complex. At the center you see the lightweight packaging waste, the pre-treatment, pyrolysis, steam cracking, that's the entire path. And there are side processes which we implicitly also introduce into the entire treatment, but I only want to concentrate on the four larger ones on the right: cost, primary energy demand, global warming potential, and the recycling efficiency. And that's the most important parameters. And since we said we're not going to talk so much about cost, I'm leaving that out. Of course, you can also talk about the treatment cost for these processes. So what's important is the energy demand and CO2 potential and how much is being recycled at all. And let's stay with this path on the next picture. It becomes a little clearer. So you can see mass flows through such a process for lightweight packagings, 12 tons per hour. That's a 100,000 ton annual sorting plant. That's what you see from that's modern state of the art. And in the sorting plant, some aspects are excluded already. So you see the bottom right, all the minerals, some organic fractions. Also humidity is excluded. That's a pre-treatment step here. And then afterwards you get an RDF. And that's a refuse-derived fuel. And you see also the metal fractions and non-ferrous fractions, which are then separated from the entire flow. This refuse-derived fuel, this RDF MK53, for example, in the LCA, that normally goes into the energetic recycling. And that's the basic material for pyrolysis. In our case, it's a separating process. I already said it. So it's those minerals and other fractions, they land in a solids fraction, and gas and condensate are the usable pyrolysis products which you then process. And they are led to the right of this process, and other fractions are used energetically. You can see that in the entire material balance. And on the basis of this balance, I showed you that meanwhile you can also measure how these material balances for pyrolysis are for the different materials. We can then do some scaling, because plants in industrial scale do not yet exist, but you can extrapolate, of course. And the calculation that we used here led to a considerable part of energetic recycling, not the absolute optimum that I showed you before, but a realistic case study. And now I'm going to show you, I think it is the last chart already. This is an overview in the form of a table for different scenarios, and the scenarios correspond to what I showed you before in the pictures. So mechanical, chemical and combined recycling, a combination of mechanical and chemical recycling. And the values that I'm going to mention are always comparing to the virgin product on a crude oil basis. And for mechanical recycling, we have two scenarios. One for 42% utilization, and theoretically there is the possibility that with modern sensor-based sorting plants you can have such a high share of plastic granules can be sorted out, but with some possible quality issues. Today we see, and this is why it says 22% here, that approximately 20% of the plastics materials from the yellow sack or bag are then new granulate, and this is the figure that we used as a basis for our calculation. So CD, that's the energy demand in megajoule per kilogram input, always compared to a plastic on a crude oil basis. So we took polyethylene here, but also other plastics were analyzed, and you can see that chemical recycling and also the mechanical recycling and the combination are advantageous compared to the crude oil-based product, as we've heard before. And you can also see that the combination of mechanical and chemical recycling, of course, is or shows the most positive energy result. With the global warming potential, the CO2 emissions, you also see that these options show low values, and that is always process specific in terms of the emissions. You might remember, we've heard it before, if you have 1.8 kilograms of CO2 per kilogram of crude oil, and here it is much less, much lower values in these recycling paths. And all these recycling paths expressed as a carbon mass landing in new plastic are shown on the right. That's the overall carbon efficiency, 42 for 22%, and chemical recycling is 60%. We already heard that for the two plants of Plastic Energy and Quantiful, they had 75%, but they are not on the basis of these totally mixed wastes. as we have observed here, if you combine mechanical and chemical recycling, then you can achieve very high recycling rates. And I now have summarized everything briefly of these studies, or the work that was at the basis of this study, and that's my last chart.
So here you can see a brief overview on the technical assessment of combined mechanical and chemical recycling, a study conducted by the Industrielle Ressourcenstrategie think tank. They were active at KIT, and here categories: energy, CO2 emissions, costs. I could comment on this as well, but I will leave it. Maybe there is a question referring to this. Energy demand, mechanical and chemical recycling have a low energy demand, mechanical even lower, and plastics on this basis, of course, are more advantageous than production based on crude oil, CO2 emissions. Here the same applies. Saving CO2 emissions by mechanical and chemical recycling, enormous opportunities here. If we look at recycling quotas, recycled carbon mass, if we consider what Germany wants to reach, 63.5% recycling quota for packaging materials, it can be a combination of mechanical and chemical recycling to reach this goal, in theory, if we don't have any design for recycling products. And of course, we could continue here for other composite materials, which are not packaging material, where you can almost sort nothing. This would be possible by way of chemical recycling. But we only looked at this on the basis of pyrolysis. Of course, there are other chemical recycling processes for specific types of plastics. Okay, let me finish here. Thank you very much.